In order to help you better understand how torque can be analyzed and the information that it can provide, I've thrown together three examples which I'll walk you through within this video. It starts with a fairly simple traditional torque problem with a father and his children on a seesaw, and then it progresses to a more intermediate type problem and one that some students tend to find a little bit more difficult. So I'll explain the process that I've gone through so you'll have some examples. I would highly recommend you copy these into your notes. But that's up to you. And this video will be available throughout the duration of the marking period. So to get on with the problem, if we take a look at this first problem, a father who has a mass of 95 kilograms sits on one side of a seesaw, and he's located 0.8 meters from the fulcrum. His daughter, who has a mass of 50 kilograms, sits half a meter from the fulcrum on the other side. The question is asking how far from that fulcrum must his son, who has a mass of 55 kilograms, sit in order to balance the seesaw. The number one thing I always recommend, always draw yourself a diagram. If you draw yourself a diagram and label it with as much information as possible, it's going to simplify every future step. So that's what I've done down here. I've drawn my seesaw with the fulcrum, and I've labeled everything that's going on. I have the father, who's sitting about zero point 0.8 meters from that fulcrum. I have the daughter, who's sitting at 0.5 meters from the fulcrum. And then I have the son, who's sitting some unknown distance. The daughter and son are on one side, the father is on the other. As with any of these problems, we always want to make sure that we calculate our forces first. So as you can see, the force of the father, daughter, and son are very simply just their masses times 10, which is an oversimplified acceleration due to gravity. So as gravity pulls down on this mass, it's going to give that object weight or force of gravity. So the father has a force of 950 newtons, the daughter has a force of 500 newtons, and the son has a force of 550 newtons. These distances from that fulcrum. So once we have the forces, we just have to balance out the torque. And I'll try and get the diagram in. So you can see here that the sum of the torques, when I add all the torques spinning in one direction, such as counterclockwise, and I add them with all the torque that's spinning in the clockwise direction, that should all come out to zero if we're assuming that equilibrium exists, which is what they're saying here. They want to balance the seesaw, so equilibrium has to exist. So if I take a look, I've decided to define clockwise as my positive torque, meaning any force that tries to spin this seesaw clockwise is going to be considered positive. Any forces that try and spin this seesaw counterclockwise are going to be considered negative. So if I add these up, I get the negative torque from the father, and I had the negative torque because if this is my fulcrum, and this is the one spot that's pinned down, if I ignore the daughter and I ignore the son, I'm only concerned with the father. Well, if this is a seesaw and I only have the father pushing down at this point, hopefully you realize that this seesaw is going to try and rotate counterclockwise. The father's force is trying to get this seesaw to rotate counterclockwise. So that's why he has a negative torque. The daughter and son both have positive torques because they're both on the same side. And if I pin this down here, both the daughter is trying to make this spin clockwise and the son as well is trying to make this entire system spin clockwise. So I have two clockwise torques generated by the children, which would be positive, and one negative generated by the father. So if I plug in my known variables, well, the negative torque on the father is really just the force times that perpendicular distance. So the force of the father is 950 newtons, and he's a distance 0.8 meters from the fulcrum, or from my axis of rotation. I'm going to add to that the positive torque of the daughter, who has 500 newtons of force acting 0.5 meters from the fulcrum. And then to that, I will also add the son's torque, which is also positive. He sits some unknown distance from the fulcrum, but we know his force is 550. So if I sum all those up, negative 950 times 0.8 plus 500 times 0.5 plus 550 times x must all balance out and equal 0. The only way that's possible, if I solve for x, is if x is in fact 0.93 meters. So the son must sit 0.93 meters from the fulcrum on the same side as his sister. It's the only way that equilibrium will exist in this situation. So just remember the general, not always, but the general idea with these problems is calculate your forces and then make sure that you sum the torques properly with the right direction, clockwise, counterclockwise, and it should add up to 0. Here we have a second example, a little bit trickier. You are designing a sculpture which consists of a steel beam and a small statue perched on one side of a fulcrum. The beam has a mass of 150 kilograms and is 5 meters long. If the statue has a mass of 60 kilograms and is placed on one side of the beam, where must the fulcrum be placed in order for equilibrium to exist? Now again, I always recommend drawing a diagram, and that's what I've done here. I have a 5 meter long beam, and I have a statue placed on one end. Now we don't know where the fulcrum belongs, so I'm going to call that x. Whatever distance, in this case from the left side or from the statue, that fulcrum should be placed, I will call x. I know the beam is 5 meters, and I know that the beam's force, its force of weight, will always act at the center of gravity. So that will act 2.5 meters from the left side because that's half of 5. So I know the beam acts at 2.5, I know the statue's on the left, and I know the fulcrum must be located some distance x from that statue. As can be seen here written in blue, that leaves this distance from the fulcrum to the beam. Well, if this is 2.5 meters, and this is x, this distance must be 2.5 minus x. It's this entire 2.5 distance minus this x, which leaves me with this piece. So I now have my forces, and I now have the distance to each force in terms of x. So as we've done previously, I'll calculate my force. The statue has a force of 600 newtons. The beam itself has a force of 1,500 newtons. And like we did before, I will calculate my torques, clockwise being considered positive. Well, if this is pinned here, that statue is trying to make this whole system rotate counterclockwise, therefore a negative torque, and the beam, since its weight acts at the center of mass, is trying to make this whole system spin clockwise, therefore positive. So if I plug in my numbers, negative 600, which is the force of the statue, times whatever distance that force is from the fulcrum, plus 1,500, which is the force of the beam, times that distance, which in this case is 2.5 minus x, must equal 0. If I distribute that out, I get negative 600x plus 3,750 minus 1,500x must equal 0. And if I just go through and factor that out, I will in fact find that that distance of the fulcrum from the one end that has the statue must be 1.79 meters. So all I did was solve here in terms of x, and then I used the equations we've already discussed, and I solve in terms of x. Slightly harder problem. You'll generally only run into that when you need to find the distance to the fulcrum. If it's a distance of a force, it becomes usually significantly easier. You really only have to solve in terms of x when you're trying to find the location of the fulcrum, and maybe in some more advanced types of problems. The third and last problem, this is one where you don't actually have a fulcrum. This is when you have some kind of structure. And we'll take a look at these moving forward as well. So I wanted to make sure you have yet another solved out example along with an oral explanation. So if we look at problem number 3, we have a bridge supported on both ends, supports a vehicle parked 10 meters from its left end. The bridge is 30 meters long and has a mass of 1,300 kilograms. What are the forces that are acting at either end? And we're going to assume the car has a mass of 2,500 kilograms. So I'm going to describe the little diagram that I've drawn. What we have here is we have a 30-meter bridge. We know that the force of the bridge will act 15 meters, or at the center of mass, at the center of that bridge. We know the car is parked 10 meters from the left end. Now I've written support A and support B here because it's a bridge. So what you have is some kind of column, some kind of wall, something that's holding either end of this bridge up. It's like if you were trying to hold a meter stick in your hands, you'd have to exert an upwards force at either end, otherwise that meter stick will just fall to the ground. So these supports are just whatever is holding this bridge up at either end. So what I've done is I've gone through and I've calculated my forces. We know the force on the car is 25,000 newtons, and the force on the bridge is 130,000 newtons. The force at support A and the force of support B are unknown at this point. We don't know what they are. We don't have enough information to record that just yet. But just like our other problems, we will go through and we will analyze our torque. Now the problem here is I don't have any kind of fulcrum. So what I'm going to do here is I'm going to choose one of my supports as my reference point, and that's going to allow me to eliminate one of them and solve for the other. And I'll show how I do that below. So I decided to choose support A, and this will be my reference point. So I've calculated my torques at support A. So everything is in relation to support A. Any distance, perpendicular distance that I calculate will be the perpendicular distance to support A. There is no fulcrum in this problem. So what I've done here is I've summed my torques about A, that's my reference point. Anything that's trying to generate a positive spin will be considered, anything generating a clockwise spin will be considered positive. Anything trying to generate a counterclockwise spin will be considered negative. So if we look at our diagram, I have torque A, whatever torque is generated here, plus the positive torque from the car, because if this is the point that I'm going to pin down, so to say, if I ignore all the other forces, this car would like this bridge to rotate around A. I also have the positive torque from the bridge, because the weight of the bridge will likewise, if I pin A down and A is that axis of rotation, or A is that fulcrum, so to say, if I pretend, that bridge will want to rotate the force of the bridge will want to rotate the entire bridge clockwise. Last but not least, support B. Well, if I'm pinned down here and this is pushing up, it's going to try and rotate that entire bridge counterclockwise. So you can think of support A here as like a hinge. It's not really a hinge, but we can assume it's a hinge. The car will try and spin around that hinge clockwise. The bridge will try and spin clockwise. Support B, since it pushes up, will try and spin counterclockwise. And that's where these positive and negative torques come from. Now, if I plug in the forces and the distances, you see what I have here. I don't know the force at A, but I know that the force at A is acting exactly 0 meters from point A. So that torque will cancel out. There is no torque. The car, which has a force of 25,000 newtons, is located 10 meters from my reference point. So 25,000 times 10. The bridge, which has a force of 130,000, is located 15 meters from my reference point, support A. And I'm going to subtract, because of the negative torque, the force acting at B, which is unknown, times the 30-meter perpendicular distance. And when I set all of it equal to 0, as is required for equilibrium to exist, I can solve that out, and I'll find that the force acting at B is somewhere around 73,333.33 newtons. Now, at that point, we know this force, we know this force, and we know this force. We don't know the force at A. And in order to do that, we just have to go one step further and sum up our vertical forces. If I sum all the forces in the y direction, since this bridge is not moving, everything should add up to 0. I've assumed anything pointing up is positive, and I've gone through and I've said the force at A is positive because it's acting up. I'm going to subtract the force of the car and the force of the bridge because these are two forces that are acting down. And I'm going to add the force at B because that force is also going up. I'm taking my two upwards forces and subtracting from them my two downwards forces, and that must all equal 0. If I plug in my known values, I wind up with this equation, and when I solve that through, the force at A is somewhere around 81,666.67 newtons. If you don't have an actual fulcrum and you don't have an object that's rotating, it's something more like a structure, like the bridge in this case, you're typically going to have to do this one additional step after you've calculated your torques and determine what missing force in the vertical direction can I solve for, given the variables and given the forces that I know.